relatively short one. And for those of you who are on the presentations, you have it on the agenda, but we're starting on page 216. Will be this PowerPoint presentation. Yesterday we talked about deep foundations, piling, where the soils are somewhat soft. We want to go down and get bearing on piling that on some ground that's further down. Spread footings are different. There's no piling. So where do you guys think that we might be able to utilize spread footings instead of a pile foundation?
Bedrock.
Bedrock. Very solid. It's been there. It doesn't move. What else?
Gravelly granular.
Gravelly granular, especially if it's dense. There could be some sands that get kind of soft and whatnot. Yeah. So those are a couple of perfect examples of where we would use spread footings. Spread footings do get used. Our sample bridge plan does not have any. I've actually thought we should probably just make one of the abutments a spread footing abutment, so we have something in our class plan, but so far we haven't. I would say on the foundation recommendations that I wrote when I was the Metro Region bridge engineer, I don't know, less than 10% for sure, probably only maybe 5% of bridges, at least in the Metro, utilize spread footings, but they do get used. And also sometimes you'll see them on retaining walls, especially if they're not very tall. So we can get to see them. So the purpose of the foundation is to transfer the load of the structure to the ground. We can do that through piles, as we talked about yesterday, or spread footings. Two different methods, but in each way, the load that's out on the bridge, coming through the deck, through the beams, down to the pier or the abutment, down through that to the footings, and then from the footings either to the pile or to the spread footings. So there are some things that control, and the main specifications that we'll be looking at here today are 2106, which is excavation and embankment. They used to be split up into 2105 and 2106, so those of you who've been around for a while may remember the 2105. But now everything's under 2106. And then certainly 2401. We've already heard about 2401, so we're going to get into a little bit more here today and in the following days. And then 2451, structure excavation and backfill. So all of those things will kind of work hand in hand as we build our spread. So what kind of things do we need to do prior to starting excavation? Especially if there's something that we're paying for excavated volume, we'd want to have cross sections and levels on that existing grade. And then clear and grub in accordance with 2101. So I think Andy mentioned that yesterday, or maybe the first day. What's the first thing we do? It's often clearing and grubbing. There's one lesson learned. Think about clearing and grubbing. Know what the limits are for clearing and grubbing. On St. Croix, we're crossing a national wild and scenic river. One of the very first days of the project, we were out there, we had a little on-site meeting, and the guys in the bulldozer, yep, I'm ready to go, and I'm going to go right down to the river, and I'm going to clear every tree that's in the path. Not so quick. There were some environmental requirements that we had to save trees from the river to I forget, 50 feet or something. So there was a number of trees that we had to save, and I'm just really glad that we had a meeting before the guys on the bulldozers got going. So be aware of that. Are there some limitations? Is there something that you need to save? Even in something like clearing and grubbing, it's not as easy as just going in there willy-nilly and and going. Sometimes there are things that have been agreed to. So the cut stakes then can be used by the contractor and inspector to say, where is our bottom footing going to be? Where do we need to go? So Adam mentioned some of those stakes with offsets, and one guy couldn't read the stake. He thought it meant degrees and it was feet and whatever. Just be aware of what you have, and that it properly guides the excavation, and it enables you to position the footing in the correct location. Obviously, that's what we want. We need that to be in the correct location. So what might we say when we talk about spread footing advantages? I can't remember, there's another slide coming up. But what are advantages to spread footings compared to a pile peak foundation? Cost is one.
Faster.
Time. I heard something else.
Faster.
Faster. Yeah. So time is money, right? And also then the cost. If we're driving pile and we're putting 60-foot piles down, we got 50 of them in the summer. It takes a lot of time, plus obviously a lot of money. You're driving, 50 sticks of steel and filling with concrete, whatever. So all of that is something that we can play. So yeah, those are all advantages for spread footings. What are some of the potential disadvantages? Stability. Why?
You're not driven in deep into the ground.
Not driven deep in the ground, and so if the upper soils are soft, what might happen? Could tilt, sink, settle. Yeah. So here's some pictures of some of the things. So if there's hard bedrock, very dense soils, those are a perfect way to use it. It's going to provide a good support. And so they are more economical, they're faster construction, simplifies the process. So you're not in there having to stage a pile of the rig and so forth. So the primary function is to spread that load out among the footings. So the footings are designed to kind of balance. And the way an abutment is designed is we can think of a big wall, and the soil behind that wall is trying to push laterally. So in essence, it's trying to push that abutment over. So the back of the footing on an abutment is always going to be wider than the front part. So the front part will only stick out past the front wall a couple feet. The back is going to stick out 8 feet, 10 feet, 12 feet, some number. And the weight of the soil that's behind the abutment is not only pushing laterally, it's also vertical load, so it's helping to balance. And so as in bridge design, that's what the designer does. They balance that, where the stem is compared to how far back and how far in front it is. So they spread the load, and it needs to be within the load carrying capacity of the soils. So as we already have heard, you get something like bedrock, it's very stable. It can take an awful lot of load. Well, granular soil can too, sometimes. But there's other soils that are pretty weak, so we just need to be aware of what that is. Pressure is a force per unit area. You're well aware of that, either PSF or PSI or something. And so it's a force per unit area which the footing can exert on the soil. In bridge engineering, we often use the term KIP, which is 1,000 pounds. So if you ever see a KSF, it means it's 1,000 pounds per square foot. KSF, 1,000 pounds per square foot. So that's something that's you tend to see instead of PSF in most cases. So the bearing capacity then is the load which the soil can withstand prior to crushing or shear failure. And that essentially means the soil can only support so much. And it's like anything. if we go out snowshoeing in the winter, and we have a little tiny pair of snowshoes, we're gonna sink in pretty far. But if we get a bigger pair of snowshoes, we're gonna have a more solid base, we'll sink in a little bit, but not as much. Same thing we're doing with bearing capacity. And then settlement is the amount of deflection that occurs when soil is loaded. There is going to be deflection, and we could say then settlement, even in steel piles. There's going to be a little bit. And there's going to be a little bit maybe because the tip of the pile goes down when it gets loaded, and also the pile itself. So any material will have little properties. It has properties that it will compress, or sometimes it will extend depending on how it's loaded. So how do we determine soil pressures? It's through investigation of surface and subsurface. It's boring, site data, various soil tests. Anybody work on a soil crew ever? It's kind of an interesting job. I had one of my jobs as a grad engineer up in Duluth. I started with MnDOT, was up on Highway 1. And we used to drill, and we're drilling on that road, and it'd be like 12 inches of bit, 12 inches sand and gravel, 8 inches wood, 20 feet of peat, and then you get down to something. But anyway, I always remember that, and we're building roads over that stuff, and it was what they called corduroy roads. It's kind of like a tangent, but that's how they literally built the road. Is they cut down trees, stacked them along the road, and then came along for a little gravel and a little bituminous at some point, and that was the road. But with bridges, we're not building on peat, we're not building on corduroy timber, but you could. Old bridges probably did. They probably just, threw one log down on the bank and another one on the other bank and put another log across it and called it good. So we nowadays would use all those boards. So this is just a little depiction of the different types of failure that we can see and the kind of things that we design against. So one is global stability. So this little diagram stuff will move a little bit as we go, but global stability means this whole mass of soil is going to go. So some of us have probably seen some of the slides that happen on, maybe it's some due to some wet conditions or whatever, but this is similar. So in that case, global stability, everything will go. The next one is a bearing failure where the shear, the soil actually would fail in shear, the particles would slip vertically against each other. So tolerable settlement, we can accept up to 1 inch. It's called serviceability. It's how does the bridge act when it's in service. So the middle one is going to show that abutment goes down. Well, the girders, they'll probably go with it, but we also then could go in, we could shim up that bearing and do different things. So we're never going to see 0 inches, but we want to keep it under 1 inch. We want to keep it from a point where you're going to put additional stresses in there. And then sliding, as we can imagine, that's going to mean the abutment goes forward. So again, there's a lot of lateral force that's coming from the soil, and it's trying to push that way. And so sometimes it would slide, and sometimes this one's going to show overturning. That same force would cause the abutment to overturn. So those are some of the things that in design we are looking for. So some of the things, the soil has capacities that range typically from 2 to 20 tons per square foot. Tolerable settlement is 1 inch, so that is the things that we want to keep. So what kind of options do we have? If we think we're going to build a spread footing and it just doesn't seem to be working, the soils are too difficult, we always have the option to change to a pile supported footing, or you can go into a larger spread footing. Obviously, that's a change. It's going to take time. If you change to a pile, you're going to have to order piles in. It's going to be contract will claim additional time. It wouldn't be easy, but it's something that could be done. You can also perform soil bearing tests if they are not in the contract already. These are things would be good to call the regional construction engineer if you ever have questions. You're building a spread footing, what's going on. So I recall one that was up in Anoka, in the sands in Anoka. We're building spread footings. It was a pretty wet site, and the inspector called me out and said, come help and take a look. You know, do we really want to build a spread footing on this site? I went out there and yeah, it looked a little soupy, but we did a little bit of dewatering and it seemed like it's going to be just fine. And it did. We built the spread footings. The bridge has been in service. I never did notice ever any settlement issues on that bridge. So ultimately it did work out. Make that call to regional guys and they can help determine if that is indeed right. So if we need, we can go to pile supported footing as shown there. So we're going to build a spread footing. What kind of things can we inspect in this picture? The forms. Ready? Are we ready for forms? Survey stakes. And what from the survey stake can we kind of check? Elevation and offset. So there's a survey stake up here, and it says it's offset 12 feet to back of whatever meter needed to working point. But run some numbers. Have they excavated far enough? What if the form is supposed to be right here, a 4-foot offset? Well, you say, this is not far enough. What else could it be? The density. Yeah. What is that type of soil? Is this what we're expecting? Do our plans show whatever kind of soil? This looks like a granular soil, really good granular loamy soil. So yeah, are all those things good? So survey stake. What's the offsets? Elevation and offset from there. Footing dimensions. Are we excavated to the right location? And then what's the soil type? Is this what we are anticipating? So all of those things can be done, and then has the compaction been done? Is it ready to set the forms and go in? So they're all things that we can look at. So in our spec book, 2451.3B3A, this is on page 447 of the 2020 spec book. So if we just open the 447, we'll see the information that's here. And essentially it says, if placing concrete on natural soil without piling, shape the bottom to the dimension and elevation. And that says, use vibratory methods to compact the foundation soil in accordance with 2106.3G. Okay, so 2451 isn't the total things we can do, because that's referring us also to 2106. And so we'll look at that here in a moment. And it also tells us to replace unsuitable soils with material as shown on the plan. And if they've unnecessarily removed stuff, it's the contractor's responsibility. So that's the spec. But among the things we want to realize is that it's turning us to 2106.3G. So that brings us to the question, what is the required compaction for backfill of structures? And how are we going to find that? So when it says use vibratory methods to compact foundation soils according to 2106, who can tell me what is the requirement to compact per 2106?
100%.
100, better 100%. Okay, so let's see what we can find. So again, just taking different parts of the spec, uniformly compact each lift according to 2106.3-4. So let's bring up 2106.3-4. That is on page 132. Page 132 of our spec book has a little table there up to the upper part of that page. Table 2106.3-4. And there's a couple of different things, material, such and such, and then location. And so the location, the center column there, all depths and locations, greater than 3 feet, less than 3 feet, and then all depths within an excavated trench and backfilled structures, 2451, structures excavation backfill. And it gets us to 100% in the right column, 100% specified density. And so those are all things that we would be zipping back and forth between the spec, what things we need. So we see from that it's 100% specified density. Okay, any questions on that? So basis of payment. So in the spec book, I mentioned this briefly the other day, in the specs and in the pay items, we have a spec item number. So in this case, we're paying under 2451. And every single spec is going to be this way, where section 1 or 2451.1 is going to be a description of what's in that. 2451.2 is going to be materials. What are the materials that are referenced in that spec? 2451.3 will be construction, and what is the construction part of that spec? 2451.4 is going to be measurement kind of stuff, and then 0.5 is going to be payment. So every single spec is going to be that way. So if you're ever looking for that, and where is that in the spec? That's what that payment system is. So for this one, basis of payment, for additional required excavation depth. So we say excavate to elevation and put your footing at elevation 900, and there's some unsound stuff that they end up taking out. So it says the department will increase contract unit price by 25% for additional excavation of 3 feet below excavation. So greater than that, you would need to then have extra work and in accordance with 14.2. Unless the department contractor can agree. So essentially that's just saying is, contractor, you're not on the hook that if all of a sudden you need to excavate 10 feet down, then you got to do it all for the same price that you said you're going to do for original. We're not going to require that. So the spec book says, here's how you pay for it if it gets 2 feet.
Does that include then material putting back in, or is that material you put back in extra also?
Yeah, that would be extra also. Yeah. Yeah, so take out and put back. Okay, for footing foundations located in solid rock, you remove the rock, the elevation shown for the entire area. If plans don't show a footing elevation, remove to an elevation no higher than the established elevation for the bottom of the footing. So this is just saying, how you excavate, and particularly here in solid rock. So again, here are some things. So we're getting ready to put some rebar in. Are they ready to put rebar? The center thing in here is called a shear key. And so you'll see this sometimes in retaining walls and occasionally in abutments. But its purpose is literally like a shear key. It's helping to, against that sliding type of a failure. It provides an additional little block down there. That thing will get reinforced. It's not just unreinforced concrete, but it'll be a reinforced zone. And as you can see there, there's some forms that'll have to get left in place. Obviously, you can't strip that. But those are things that they look for. So look for that keyway. Is the grade correct? And then where's the pour line? Where are we going to pour to? They have some grade nails or chalk line, whatever. They have something to show where is that top of footing. You can also look, of course, the soil type. You can look, this is a case where we're building adjacent to a railroad, so as you're building, make sure that whatever provisions are for the railroad. It's kind of a weird picture. Looks like you're almost right on top of the railroad, but it looks like maybe it is up an embankment and it's far enough away. But to make sure whatever protection for the tracks are there is done. So we do need to use forms for all concrete except if you're in solid rock. So that means we can't just let the contractor go, well, I'll pour 6 inches, I'll give you 6 inches of concrete and I'm going to pour against the dirt over here. No, why wouldn't we? You could get cave-ins. And so then all of a sudden you have intermixed with your concrete, you can have some soil that cave in. So we do not allow that. There's oftentimes things like retaining walls, especially. You're going to have multiple activities. Here there looks like they're starting to pull some cure so they can run some rebar. Here they're got rebar in. They're ready to cast some concrete. Down here they're haven't yet put rebar. So many different activities there. Curing is important. We're going to talk about that in this section and many different sections as well. So when the footing is to be placed on a recently constructed fill, we need to think, is there a waiting period? So even though we don't have spread footings on our bridge, there is a waiting period. Anybody remember from the front sheet and what Andy talked about, what's our waiting period before we can start building? 72 hours on this one. So just think, is there a waiting period? Is there any other kind of thing? Do we actually have to build not only to full height, but we need to surcharge it some additional. So be aware of what you have. And so then settlement plates might be required, and we spoke a little bit about that, depending on what we need for our settlement. So some additional requirements in 2106. You compact to 100%, we already talked about that. And then there's a requirement of the structural backfill. The maximum lift thickness is 6 inches compacted or 8 inches loose. So they put the loose material down and they run their compaction, and it should be no more than 6 inches. So those are, that's not just something that you as the inspector say, yeah, you never go over 8 inches. Well, it's in the spec. So those kind of things, just be aware of where it is in the spec, and then the contractor doesn't have a. Here's some pictures. This one is the Rochelle pit up in Virginia, I believe. And a lot of great granular material. I mean, they're mining this stuff for years. This was when we built this bridge, because the old bridge was actually on MnDOT leased the area for I think 40 years or 50 years or something from the mine, and there was still ore under that old bridge. And the mine said, sorry, we want our land back. And so this whole new bridge up there is a result of that. So MnDOT lost its lease after 40 or 50 years, built a new bridge, but nonetheless it made for some some good materials for building. So here's some 24-inch minus embankment for a spread footing. In this case then, there was also some rock, some bedrock, but we see it's kind of on a slip plane, we might say. The bridge is off to the right, and so they filled with a fill here and then cast the footing on top of that. So spread footing, but on a little leveling pad here that was. And then after the leveling pad was placed, then they'd come in and do the typical forming. So that's on a very sound foundation. So obviously then there's going to be all the rest of the things that you guys as inspectors do, which is test the concrete. If there was any soil bearing tests, we could do them. This one obviously doesn't need it. But then test the concrete and monitor the placement. So here we also, as we're doing, whether it's a spread footing, a pile supported footing, or whatever, we want to know what is our distance that we're supposed to come out of the footing. So sometimes it's simply what is the lap length that we need. Other times this bar might continue up, and then the next one might lap starting 5 feet up, just to try to minimize some steel or whatever. But pay attention to that, and obviously pay attention that they're also in the correct location. So soil boring cores, so when they get in rock, they save the cores like this, and the geotech engineers are able to make a determination of how sound that rock is, what kind of capacity it can hold. And so then when you guys are monitoring and watching an excavation and the construction, you see what is the type of soils that are encountered. Is it what we are anticipating? Is there a water table somewhere that we have to hit? And is that water table higher than anticipated? And is there any soil stability issues? So also then keep track, not just perceiving, but maybe make track, make some notes on the boring logs in the back of our plans. Yes, this is what we saw, whatever. And then comparing major differences. And if there is major differences, that's a perfect time to be asking the soils engineer, the geotech engineer from the lab, the regional construction engineer, what kind of things we got. Sometimes you take some little samples, confirm with these hand borings, is everything uniform? Bottom excavation looked good. Be careful with these, don't pull out your back like I did one time. It can be problematic that way, but just make sure that we have good sound material. So soil boring bearing tests are not provided. We could institute one by paying the contractor. There'd be a change order. They would have to come in and do that. But what kind of things are we to gain? So if we come out there and the soil is just absolutely a swamp, and for some reason the plan said, yep, we're putting a spread footing, probably a soil bearing test wouldn't really help at all. So all of the things, anytime we change something major like that, if we're changing from a spread to a pile, there's a lot of costs that are going to come along with it. And so we can, in some cases, maybe we can increase the size of the footing and rather than change to it. Some of the things we do before we start the excavation, compare the location of the stakes with plan location. Does everything look right? One of the things that we learned, and I don't know how we can avoid it in the future other than pay attention, but we were building a bridge that's Highway 5 over 2 212, not too far from our bridge, our sample bridge, just maybe a mile or two to the east. But we're building that bridge as concrete box girder, and the chief inspector called me one day and he said, the piers aren't seeming to be lining up. And they had already cast the pier columns, and he's looking and saying, not sure how this is going to line up. You can just see that there's like a kink in it. Well, it turned out there was a plan there, and there was a 3-foot offset that somehow was missed. And so pier 2 or whatever literally got built 3 feet off. We went in and had to undermine the pier, put like a little shear log, drive a couple extra piles, scab onto the pier wall that had already been built, and then we're able to build the superstructure in the correct location. But again, it's things that as you're going, if you can, you just keep those eyeballs open, look for alignments and things like that. We always want to check, is our elevation right, our offsets to the railroad tracks, everything right there. And then it says even structural or navigable waters should receive special attention. So everything really should. So you as inspectors, you're looking for the type of soils, compare it to what the plans show. And then what's their compaction effort? Are they getting 100% where we require 100%? Any boils or springs? And then if there's anything significant, we could revise the foundation type. So I think we have a couple pictures on the boils and springs that we always want to divert water, we don't mix it in. So when you think of the design concepts, there's bearing pressures, factor design bearing pressures that we have. We'll show on the next slide what that looks like. A factored soil bearing resistance is based on soil type. So like anything, structural design is loads and its capacity to withstand those loads. So no different in spread footing. And so it's kind of this deal, the design bearing pressure has to be less than the soil bearing resistance. So the loads have to be less than what things can withstand. So here is, if we had a spread footing in our plans, and really we should probably put this in just so you have it in the plans, but this is what it would look like. So at an abutment, you'd have a design bearing pressure number would be filled in. And this is shown in tons per square foot. I said a lot of times it's kips per square foot, so I think we can do it either way. There's an effective width, B prime, that's kind of a more design thing that they worry about within the limits of the footing, does this B prime number fit within it? So you have to concern yourself exactly of that number, and then ultimately there's a bearing resistance that will be shown. That's based on something load combination. There's different load combinations. You can have just dead load and vehicle live loads, or you can add wind onto it. You can add earthquakes onto it. You know, there's different load combinations. Then out in the field, similar to our piling, we're gonna want to say what is the bearing resistance that we have. So I guess this one is for the abutment, this one is for the pier. End of the day, we want to have a bearing resistance that is going to resist all of the loads. If you're on rock, there's something a little bit different, a similar thing, but they also look at here on the pier is what is the at each corner, what is some bearing pressure that we have. So if you have a spread footing, that's what it's going to be. I mentioned before that we will always have a larger heel of the footing back here, so that the soil, the weight of the soil will help resist overturning. The front face is going to be smaller. Sometimes it will show that you need to put some special material, and so This would say here, compact the top 6 inches of the subgrade, and then this one is talking about aggregate backfill underneath the footing. So in this case, they actually dug out some of the material, put back different, and then the bottom of the footing is right there. And so here we see, again, then a table of data that factored bearing resistance 3.16 tons per square foot. Similar picture to what we saw before. We want to confirm our locations and our elevations, soil conditions, things like that. So again, what kind of things would we look for here? So for the footing, we're going to see our forms set to the correct dimensions, our lengths, our widths, our depth of footing. Do we call for a 4-foot footing? Do we have forms that can get 4 feet of concrete? So all those things are done. Obviously, it's always better to be out here when they're doing it. So, for instance, if this inner form somehow was a foot off, and now they had to move it once you're at this stage, it's much harder to move it now than the day they put the forms up there. So the more you can be out there watching the operations, doing your checking, the better. Help the whole process. So again, looking for the stakes, offsets from working points, is the rebar in the right location. Checking pour line elevations, depths, rebar placement, and so forth. Yep, good point. I was just going to mention that these are called Dobie blocks, is the name that they use. We cannot use those in things like bridge decks, but we can use them in this situation in spread footings. And so they're little blocks that they literally set the rebar on that so the rebar wouldn't sink down. You got to keep the rebar so that concrete can get all the way around it to make it structural. But yeah, good observation. That is exactly what they're for, is to put the rebar on there. So Dobie blocks are what they're called. But again, the contractor, I have had cases where they say, well, why can't I use Dobie blocks in my decks? Well, they will be visible from the bottom. They'll also cause additional deterioration. And so, but Dobie blocks are allowed in this type of configuration against the ground to keep the bars up off the ground. They can also use other kind of chairs. Like in the back, I have some examples of some chairs that, they could use those as well. Sometimes they fabricate their own. Like this is just a bend bar, but sometimes they're like a little Z shape, or it's not even a Z shape, but some kind of a thing that has it functions as a chair that they can set that rebar on and or tie to. So just a couple of slides on if there are some troublesome springs or boils, what do? Do we mix it in? No, because what's that going to do? It'll reduce concrete strength by increasing the water cement ratio. So in structural engineering and in all concrete, we're concerned about water cement ratio. So we don't incorporate the water. It should be diverted. If there's smaller springs, we can use a canvas or something. They have to provide a dry excavation. So we had a kind of a major artesian coming up on one of our piers on St. Croix. And they ended up using what they call French drains, which essentially is like a half pipe of PVC, and then a little trench, and the water would literally flow out the trench to the corner of the footing and then pump it out. But the thing was coming pretty good, and everything worked out pretty well. We saw a couple little pieces of water, little trickles of water that came up, but we're able to keep it pretty decent. So then when they go to the side, you'd have to pump it out. Obviously here we're getting some concrete, so this isn't stuff we would put back into the river, because that's going to be concrete contaminated, so you have to be aware of how they're pumping it out and what kind of things that here's just a picture of how you might divert the water boil and keep that water out, don't mix it in. So the general specs do permit the engineer to delay all construction except foundation excavation until we have a conclusive test to determine that there's something. If there's different soil conditions, we need a change order. But we don't want to use this part of the spec to unduly delay the work. But this is just saying, if you see something out there, you're building a spread footing, call a timeout. Let's take a couple hours to figure this out. Doesn't mean you can take 2 months, to figure out the issue, but it does give you that. So we should check for settlement, is what this slide is saying. Oftentimes that's as easy as you just mark it with a magic marker on your footing or up on your stem or something, and then track it over time. And it's good information to know that are we doing any settlement or what's going on. And then movement check should be started as soon as our first stone is placed. If we're in solid rock, rock has to be removed in a manner that doesn't impair the quality of the foundation. So that's obviously we don't want to damage some of our rock that our foundation is. So just have a few slides here on soil bearing tests. Again, they're very, very seldom used. So I'm just going to run through this quickly. They may be required in the proposal, and excavation needs to be substantially completed before we conduct that. And the way they do it, and this is actually, so there's some information in our course manual, page 3-6. But we would wait until the test results have been determined before we continue on. But essentially, it's a base plate that is set. You apply loads. You hold the loads for certain durations, and then you measure your settlement. You actually go down in a series of slides. Show that. Yeah. So each load is 25 tons, and then we would hold that 25 tons at 15% of the 25 tons, 25 and so forth, all the way to 100. And you hold them until your settlement has stopped. So if you push that load on there and it just keeps on settling, it's not a good sign. But usually you put that load on there, it would settle a little bit and then it would stabilize. Then you put a little more load on, it'll settle a little bit more and stabilize. And so you're tracking all of that. And then you hold it for at least an hour. Wait till you get down to 0.01 in 15 minutes. And if you get more than 2 inches, it is a failure of the test. You remove it in reverse order, and the specs just say the contractor has to provide suitable shelter. So if we do this, if it's not required in the contract, a change order would be required. Just a little review. The 2 most common types of footings are, some start with a P, pile supported footing, and what's the one we've been talking about? Spread footings. When allowable soil pressures become quite low, rather than increasing spread footing, a more economical may be what? Pile. This is, I actually haven't really seen this. That would be a big change. And who determines this? That'd be the engineer in the bridge office. The high embankments for abutments might require monitoring what kind of plate? Settlement. Here's settlement plates. Settlement plates. Initial elevations should be taken when? Prior to any fill. So one of the bigger problems is you start putting your settlement plates up and you haven't taken the initial reading. So settlement plates and take it prior to your placement of the fill. When footing is placed on recently constructed fill, what kind of provisions? Special provisions may require a waiting period, overload, or particular seat. So again, on our bridge we have 72 hours, but there may be different things on your bridge. If we're on rock, the removals shall be in a manner not impair the quality of the foundations. Placing concrete inside a coffer dam will encounter water. Since this is common, we should ensure we have mixed the extra water into the concrete. False. Okay, and then sometimes you do it have time for the whole thing, but for cubic, again, length times width times height divided by 27 for cubic yards. So certainly even add a little keyway in there. It's, I think you guys are familiar enough with how to do that. And next one is just another finding. So any questions on spread footings and the things we talked about? Okay, I think that is that's it. Okay, so let's take